I've made some updates to my 3DP plane design project. Check out my earlier videos on this project if you haven't seen them. First, we have the Scale Master object. It's here in the Common collection that's hidden by default. I'll enable the collection and I'll select the Scale Master object. I can change the scale factor by clicking S and dragging, and as you can see, the entire aircraft is scaled accordingly. I can be more precise by entering the scale in the items panel. I'll just select the X, Y and Z and set the scale to 1.5. The intention here is to scale all the things that should be scaled, like the overall dimensions, but not touch the things that should be constant. For example, the gap between the ribs and the wing surface should stay the same. The servos and the servo base sizes and things like that. Of course, when changing the size of the aircraft by more than a small amount, there are likely to be some design changes required. For example, I may choose to manually increase the number of ribs in the wing. Perhaps I'll want to increase the diameter of the carbon spar, or choose bigger servos. I'm hoping this should make it easier to create a small prototype of a design and then test it and then scale it up to a bigger size. The 3DP plane design file now has two fuselage bisections options. The original I've renamed fuselage s.subd as it relies on subdivision surfacing for its smoothing. The base geometry node network allows any resolution around the circumference of the fuselage, but not along the fuselage. Subdivision surfacing is then applied, which increases the resolution all over and smooths the shape, but it tends to shrink the shape in the process. The amount of shrinkage depends on the resolution, so we can get close to the original shape, but that requires a high vertex count. I guess a high vertex count isn't a huge problem when it comes to 3D printing, but I can't help finding it a bit annoying. The second option is called Fuselage S Loft. Effectively, the function fits Bezier curves along the length of the fuselage, and this means the shape of the sections is accurately preserved, and the resolution can be set in both dimensions, both radially and longitudinally. One downside to the Lofted version is if you have two sections close to each other, they must be very similar or the end result won't be smooth. For both versions of the fuselage, I've added optional cut-off parameters that make a clean cut at the desired points. I found it was necessary in order to have some control of the shape of the fuselage as it approached the end. For example, you can model the spinner roughly, and then you chop off the fuselage and the shape of the fuse then blends in the correct way to the cut-off point. So in summary, both versions are still useful, depending on your requirements. The Loft version fits exactly to the provided sections, so you have to take care that these are accurate and they don't change too abruptly. The Sub-D version tends to give you a smoother result, but at the expense of dimensional accuracy. If I choose a reflective material and we look carefully at the two objects, it allows us to see the small differences between the two modelling techniques. I guess simply choose the one that you like the best. Previously, I used Blender's armature system to adjust the positions of the aileron cutter mesh. This had the downside that it forced users to have to work with the complex subsection of Blender that's really designed for character animation. Also, if the shape of the wing was altered, the control surface position would have to be manually altered as well, and that relied on a bit of sort of hand-to-eye coordination. I've replaced all of that with some more geometry nodes. The aileron cutter objects are stored in a collection that's hidden by default. I'll just enable it so we can take a look. The locations of the cutter objects are determined by a guide curve. It's meant to be positioned above the wing, and as you can see, the two endpoints then set the X and Y locations of the corners of the ailerons. By default, the vertical positions of the corners are set by the height of the leading edge curve. This isn't really a perfect solution, as the twist of the wing and the shape of the airfoil can make the trailing edge a bit higher or lower, but generally it gets quite close, and then there are fine adjustments available. For the cutter objects themselves, there are parameters in the Modifier tab. There's an inner object and an outer object, and the parameters can all be set on the inner object. Then they're automatically copied to the outer object with drivers. The names inner and outer, they don't mean too much anymore. One cuts a piece out of the wing and the other one cuts out the actual control surface. Let's run through the parameters. First, there's a link to the guide curve. Then we can adjust the size of the cutter. Really doesn't matter how big it is as long as it extends past the trailing edge. The gap parameter defines the size of the gap between the control surface and the wing. By default, the side edges extend straight back along the y-axis, but the angle for each edge can be set using the outboard and the inboard angles. The same geometry nodes are also used for the elevator and for the rudder cutters. So the rudder gap and the rudder angle are here mainly for the elevator, but they can be handy on the wing if the aileron extends all the way to the fuselage. The rudder gap provides a gap on the inside of the control surface, and the rudder angle lets you manipulate the control surface angle independently of the angle of the slot. This is how the default elevator control surface has been set up. The Z offset adjustments allow the endpoints to be raised or lowered to allow for a bit of precision adjustment of the hinge point. The inner and outer cutter shapes use the same geometry node network, so the tick boxes here just select which one this particular object is. Shrink to wing makes the guide curve drop down to the height of the leading edge curve. If you leave this unticked, well, you can set the height of the cutter manually using the guide curve. So this is how the cutter shapes are formed, but to apply these cuts to the wing, there's a modifier on the wing object, and there's only a couple of parameters. The inner and outer shapes are referenced here. The tick boxes allow you to select whether just the wing or the control surface are displayed, or both, and this is useful while slicing. I'll just enable the slicing modifier and also enable the slicer master in the common collection. Then I'll select the correct area to slice, and now I can easily select either the wing part or the aileron part to send to the slicer without the hassle of defining separate slicing boxes for the aileron or selecting things manually. Everything I've discussed here for the aileron, it's also applicable for the elevator cutter and also for the rudder cutter. The curve ribs have received just a small enhancement. There's now a distribution bias parameter in the curve ribs. By default this is set to 1, but if I reduce it to say 0.5, the distribution of the ribs will be less near the wingtip and more dense near the root of the wing. On the other hand, if I put it to 1.5, the situation will be reversed and the ribs will be more dense near the wingtip, less dense near the root. Actually, this change also made me realise the holes in the ribs, meant to produce less weight in the model, had the width set as an absolute value in millimetres, and that's not really what we want, even without this distribution bias. So I've worked on that and changed the function of the width parameter here in the curve holes object to be in percent, so 100% gives holes which are the full width of the gap between the ribs, and 50% makes them half the width like you might expect. It also helps to keep the holes the correct size while scaling the entire aircraft, which is something that didn't happen before. So that's it for the changes in this model. I'll catch you next time.